first of all, I want to thank the organizers for inviting me to speak here. It's a pleasure to be in Utrecht, well, virtually, but in Utrecht. So the first thing that I want to say is that this is a joint work with Daniel Alvarez, a former student of Enrique Burstein, as me. And what I want to talk today is about work in progress. So it's not already even in archive. So it's something that we are just starting to think about, and we have right now the first results, but we expect to be like soon an article or even in archive or whatever. So please take care about everything that I say today, because you see it's a work in progress, most of the things. So let's start. So what I want to talk is about these Stacky Lie algebroids. And let me just start with a motivation. So recall that you have the Lie groupoid category and the Lie algebroid category, where objects are Lie groups or Lie algebroids, and morphies, Lie groupoid morphies or Lie algebroid morphies. And between these two categories, we have this Lie functor that, given a Lie groupoid, associate to it its Lie algebroid. And then it is well known that this Lie functor, in this case, is not essentially surjective. So there are Lie algebroids that couldn't be integrated to a Lie groupoid, and was known, like, I don't know, 40 years ago by Molino and Weinstein of counterexamples. And like 20 years ago, explicit obstructions to the integration of Lie algebroids were computed by Marius and Rui in this case. So just a natural question shows up, that is, what is an integration of a general Lie algebroid, where Lie algebroids can be integrated? And well, 15 years ago, it was given an answer by Chen and Chen Su that said that a general Lie algebroid can be integrated to an étale Stacky Lie groupoid. So they just define what an Stacky Lie groupoid is and show that in the étale case, really, Lie algebroids can be integrated to this kind of étale Stacky Lie groupoids object. Then, okay, just the next question appears. Okay, if we drop just the word étale and we consider Stacky Lie groupoids, what are the infinitesimal objects that appears? And come on, everyone can say it just, okay, if you put a stack in front, the only thing that I need to do is to put a stack in front of a Lie algebroid. So a Stacky Lie algebroid, and we start to see it in the literature, and there is no definition of what a Stacky Lie algebroid is. It's just an object that is not already defined. It's just an undefined flying object right now. So what we just start to ask if we can define also a category of a Stacky Lie algebroids that extends the category of Lie algebroids, and moreover, if the Lie functor can be extended to this Stacky world. And well, this is what I want to do today, is just introduce what a Stacky Lie algebroid is and study the main properties of Stacky Lie algebroids. So there are two things that I want to do. One is the three items here, A, B, and C, that is more or less what we already have. And then the item D that will be really short, that is what is not done yet, but we are working in. So the tag will be a structure at the beginning in just trying to see what the Stacky Lie algebroids are, and more generally, what a Lie algebroid over a differentiable stack is. Then I will define the Stacky Lie algebroids properly, see their main properties right now that we have. And finally, I will talk about this work in progress thing. Okay, so let me just start by the beginning. So as you see, the first word that appears that maybe is different is this of a stack. What a differentiable stack is. So the idea is that for us that we are, let's say, in the Poisson community, differentiable stacks can be thought as good models for singular spaces. And this is what the idea behind that I will use it. But in fact, differentiable stacks are something different in general. So the formal expression of a differentiable stack is that you can consider the category of a smooth manifolds endowed with the Grothendieck topology given by open covers. And then a differentiable stack is a category with a functor to the category of a smooth manifolds satisfying these three properties that are not defined here, but more or less in order to have an idea is that this category is good because pullbacks exist and are somehow universal. Then we have some kind of gluing properties, and here is where the Grothendieck topology of open cover centers. And these gluing properties can be seen it as sheaf-like gluing conditions. And then we also require that this category have a presentation. So I think that this is the usual definition of what a differentiable stack is, and you can find it in many places, but for example, Behrens-Schuh is a good reference. And what I want to say is that basically the idea that you can take it is that a differentiable stack is just a category with some good properties attached to it. Then the important thing for this talk of differentiable stacks is that they form a two category. Instead of just a category, you have a two category given by differentiable stacks, where the objects are just the differentiable stacks itself. The morphisms are functors between the associated category that commutes with the projection. And then two morphisms are just natural transformation that also satisfy some compatibility. So that's the important thing in this talk, that stacks are some kind of categories with good properties, and they form a two category. But okay, I just start at the beginning saying that differentiable stacks are good model for singular spaces. So where is the geometry behind all these kind of things? So the geometry stays in a different point of view for differentiable stacks that comes from Lie groupoids. So suppose that I have a Lie groupoid, then I can define a category, sometimes call it VG, where the objects are principal right G bundles, and the morphisms on that category are just morphisms of principal G bundles. Okay, and the point is the following theorem that is some sort of dictionary between Lie groupoids and differentiable stacks. So for any Lie groupoid, the category VG or M over G is a differentiable stack. The second is that given a differentiable stack, I can construct a Lie groupoid because this category have good pullbacks, then I can construct this groupoid over here. And moreover, then VG of that groupoid is isomorphic to my previous differentiable stack that I started with. And the third point is that if two Lie groupoids are Morita equivalent, then the differentiable stacks are isomorphic, and moreover, the converse is true. If the differentiable stacks are isomorphic, then the two Lie groupoids are Morita equivalent. So the conclusion, and this is one of the most important items of this talk that we will use it a lot is that differentiable stacks can be thought as Morita class of Lie groupoids. And this is more or less the geometric interpretation. And where is the singular space that I promised you? So given a Lie groupoid, the base of the groupoid M have an action of the groupoid given by, by the source or the target. Then you have that G acts on M, and then the leaf space of that action is a singular space. And what happens is that the differentiable stack is a good model for that singular space. So that's the way how differentiable stacks are good models for singular spaces, and how differentiable stacks can be thought geometrically using Lie groupoids. Okay, so once we have the definition of a differentiable stack, then I can introduce these Stacky Lie groupoids. So what is a Stacky Lie groupoid? A Stacky Lie groupoid consists just of a differentiable stack and a manifold, and I put like a Lie groupoid structure over there. So I have one morphism, source, target, multiplication, unit, and inverse that are the structural maps of the Stacky Lie groupoid. But now, instead of the multiplication satisfy associativity, really to have a unit on the left, a unit on the right, an inverse on the left, an inverse on the right, I have that these properties are just weakened by using two isomorphisms because differentiable stacks form a two category. Then a Stacky Lie groupoid is something that I have one morphism, the same as for a Lie groupoid, but I added two isomorphisms that controls the associativity property, the unit on the left, unit on the right, inverse on the left, and inverse on the right. And then these structural maps must satisfy these compatibility properties, the usual ones plus some higher coherence for the two isomorphisms. So let me say some words about why you should care about these Stacky Lie groupoids. Maybe the first thing is that they integrate Lie algebroids. So this is maybe the first reason and the most important one. So if you want to integrate any Lie algebroid, the place where you end it is not a Lie groupoid, it's a Stacky Lie groupoid. Then this is just that is a good reason to care about the Stacky Lie groupoid. But if what you are interested is to study singular spaces, so differentiable stacks, then maybe you want to know what are symmetries on singular spaces, and this was studied by Christian Bloman, or actions on differentiable stack, Burstyn, Noceda, Su, or just Hamiltonian actions on symplectic stacks by Hoffman, Sahamar, and Su. So there are a lot of works where you need to study singular spaces that are really stacks, and then the natural symmetries of these spaces are given by Stacky Lie groups or Stacky Lie groupoids.
Why don't you assume M to be a differentiable stack as well?
Well, this is something that I will go there, but the definition given by Sen and Sun is that for Stacky Lie groupoids, in order to integrate Lie algebroids, you just needed M to be a usual manifold, because for a Lie algebroid, the Lie algebroid is over M. And there is another good reason that I will give in a moment for that. Okay, so let me give some examples. So any Lie groupoid is just an example of an Stacky Lie groupoid, because any manifold is an example of a stack. Okay, the second example is that you can consider strict two groups what is a strict group? It's a Lie groupoid where G and H are also Lie groups and the two structures are compatible. Another name for these objects is a crossed model of Lie groups. Then what happens is that the stack that these Lie groupoid models is a Stacky Lie group. It was a question or?
Not that I saw.
Okay, so then I will follow. But more generally, then instead of consider using it the base point to be just a point, I can put it any manifold M here, and then I can put it a double Lie groupoid structure here, covering the identity groupoid. And this is another example of a Stacky Lie groupoid. But okay, up to now, the three examples that I give it satisfy that the two isomorphisms given here are trivial. So are there examples of things where the two isomorphisms are non-trivial? Well, the one that integrates Lie algebroids. There, the two isomorphisms are non-trivial. So suppose that I have a Lie algebroid, then I can construct the Weisstein groupoid that is just A path modulo A homotopies, and then say and so prove it that this topological groupoid is indeed have the structure of a Stacky Lie groupoid. And the Stacky Lie groupoid have these two isomorphisms that are non-trivial in this case for a general Lie algebroid. And the last example that I want to give and also explain why the base manifold, the base of the Stacky Lie algebroid is a manifold, is this guiding theorem proved by Chen Chan that states that there is a one-to-one correspondence between Stacky Lie groupoids and Lie groupoids modulo Lie2 groupoids modulo 1 Morita equivalence. So Lie2 groupoids here are thinking as a simplicial manifold satisfying a Kant condition up to level 2. So this is the usual definition for Lie2 groupoids. And in order to have this equivalence, it's crucial that the base is a manifold, is not an arbitrary differentiable stack. So this
Miquel,
yeah.
Let me ask you something. Isn't that true also, this guiding theorem, if you consider a strict Lie2 groupoids, which are basically these double diagrams that you designed there?
If you consider a strict Lie2 groups, for two groups, I think that is not. So for this diagram,
this diagram that you have there is a Lie2 groupoid, a strict Lie2 groupoid. Okay. So
you say in this square that I have here, this is a strict Lie2 groupoid.
Yeah.
So you want
I was wondering whether you can include in this guiding theorem this also this other.
So you want to put a strict here and the strict here?
No. An equivalence between the three: the Stacky Lie groupoids, the Lie2 groupoids in the weak sense, and the Lie2 groupoids in the strict sense.
No, I think that that's not true, and this is the whole thing.
Because of the associator.
Yeah,
you can strictify the associator when it's a discrete sense, but as soon as the differential geometry enters, you cannot strictify them. And
yeah.
The best you can do is in the 8 Lie2 group case over there, even if it's Lie, but if it's 8 you can still strictify, but otherwise you cannot.
Yeah, this is maybe the whole point of what we will give, that at the infinitesimal level it is clear that the strict things is not enough, and we will propose a non-strict thing, and this is what we want to do. And at the global level, if at the infinitesimal is not true, at the global should be also non-true. And the answer is what Chen Chang was explaining, basically. You need
because, sorry, there is this NER functor that you can map every strict to groupoid to a weak to groupoid. And my impression is that this is an equivalence when you look at Morita equivalence, but I may be missing something, so sorry.
Yeah, maybe we can discuss that a bit later and see if there should work or not. Okay, so once we have the examples of these Stacky Lie groupoids, then I just will propose what a Stacky Lie algebroid is and how to use them. So the first strategy to define a Stacky Lie algebroid is just to define a vector bundle where the total space of the vector bundle is a differentiable stack, and then to try to define a Lie algebroid structure over there. So this was done somehow by James Waldron, and there are some approaches there, but was not enough in order to recover what we want. And well, we think that it's still possible to do it, and we are trying to work on that, but it's not done it right now. So what we follow is the second strategy, and the second strategy consists in to use the dictionary. So I just to pick my Stacky Lie groupoid, and then I just unfold this stack over here and pick it as representative, so any Lie groupoid, and then M is identified by this identity groupoid. And then I want to know which is the structure that this kind of square inherits naturally. And then a Stacky Lie algebroid will be some kind of the Morita class of one of such structures, whatever it is. And this is the strategy that we will follow. Okay, and then this is the first problem, this Stacky Lie algebroid. But then as Marius asked, okay, but once we are here, why we impose this to be the identity? Why we don't replace to just any different Lie groupoid here? And well, then this picture shows up. And basically what this happens is just trying to define Lie algebroid over differentiable stacks in general. So what is the picture? Let me try to explain here. As we seen it in the square, you seen it at the beginning, I put these arrows to be non-dashed. If the arrows are non-dashed, that means that what you have really is a double Lie groupoid structure over this square. And then if G is equal to M and the arrows are dashed, I want to say that this is what the Morita class of this is what corresponds to a Stacky Lie groupoid. Then there are like two directions. The Stacky direction where the arrows are dashed, and the double Lie groupoid direction where the M is replaced with an arbitrary G. And then you want to unify these both directions. And this is what should be a Lie groupoid over a differentiable stack, or what we call a quasi-double Lie groupoid, that there is no definition right now for that. And then if you apply the Lie functor, then for Lie groupoids, you end it in Lie algebroids. For double Lie groupoids, you end it on LA groupoids. And for Stacky Lie groupoids, you end it on Stacky Lie algebroids. And the more general,
Miquel,
yeah.
Excuse me, what is the meaning of the dashed arrows here?
Well, the dash arrows should mean somehow generalized morphism between Lie groupoids.
Okay, thank you.
But there is no explanation right now of what does it mean. But the thing is that we want to just, this dash thing includes one morphism and two morphisms in the level of the stacks. And then at the level of Lie groupoids means generalized morphism. can be also thought as, you know, principal by bundles, or so there are different ways of making sense of that. But basically, the point is to make sense of that because there is no definition right now. So I will focus into this general thing, into the general object here of these quasi-LA groupoids or Lie algebroids over differentiable stacks. This is what I want to define, and then we will show that in the case where G is equal to M, where you have here the identity groupoid in the base, then we have the definition of a Stacky Lie algebroid. So this is more or less the whole strategy that we will follow. Okay, so let's go to the second part. That is just defining a Stacky Lie algebroid via these quasi-LA groupoids. Okay. So the point is that this definition of quasi-LA groupoid appears previously in the literature in the case where G is equal to M and both are equal to a point. And this is the notion of a semi-strict Lie algebras given by John Baez and Alicia Krantz. So what is a semi-strict Lie algebra? A semi-strict Lie algebra is a two-vector space. So it's just, you know, a Lie groupoid where this L1 and L2 are vector space and everything here are linear maps, endowed with a bracket that is a skew-symmetric bilinear functor and an antisymmetric trilinear natural isomorphism that controls the value of the bracket being Jacobi. And this trilinear natural isomorphism satisfy a compatibility relation with the bracket that is this more or less complicated equation. Okay, and why we know that this is the right answer in the case where G equal to M equal to a point? Because they have this theorem that say that there is a one-to-one correspondence between semi-strict Lie algebras and two-term L infinity algebras that I will define later. But this is, you know, the object that the infinitesimal object that corresponds to Lie groups, and then they satisfy this guiding theorem of Su. So now the only thing that we should do is just replace this by our object. So replace a two-vector space by a two-vector bundle, so a VB-groupoid. And now I want, you know, the bracket to be a functor and a natural isomorphism controlling the Jacobi. But we have a problem that for Lie algebroids, the bracket is defined on sections and therefore is not a functor. So we spend a lot of time trying to, you know, see how to solve this problem. And then we just show it that what we need is to think on another way, Lie algebroid. And then graded geometry helps you because there is a one-to-one correspondence between Lie algebroids and degree 1 Q manifolds. So basically, instead of thinking Lie algebroids as Lie algebroids, you think Lie algebroids as the associated differential complex given by the stereo Chevalier-Eilenberg differential on the weight of the stereo algebra of your vector bundle. So why this is a new point of view that helps us? Because there is this second theorem that says that there is a one-to-one correspondence between VB-groupoids and degree 1 Lie groupoids. So this is just Lie groupoids in the category of degree 1 graded manifolds. Moreover, was seen it by Rush that LA groupoids, so VB-groupoids that are groupoids in one direction and Lie algebroids in the other, so the infinitesimal objects of double Lie groupoids are in one correspondence with degree 1 Q manifolds, with degree 1 Q groupoids. So what is a degree NQ groupoid? And here is the important thing, is that it's a groupoid object in the category of graded manifolds. So G and M are graded manifolds. And now the Q is just a degree 1 vector field on G that satisfies two conditions. The first one is that squares to 0. That is, if give you a Lie algebroid structure on G, or a Lie algebroid structure over G. And the second is that its compatibility is compatible with the groupoid structure. That means that you have a groupoid morphism from G into the tangent shifted by 1 of G. So right now, we are able to see the bracket of Lie algebroids as a functor between two groupoids. So two different groupoids, G and T1 over G. And right now, since we have a functor, we can do natural transformation between that functor. Then this is our definition, and maybe the main definition that we propose is what are these degree and quasi-Q groupoids. So I have two graded manifolds of degree n, M and G. And now I have Q, that is a vector field on G of degree 1, but I have also alpha, that is a section of the Lie algebroid, but a section of degree 2 of the Lie algebroid. And the compatibility is the following. Q is a groupoid morphism. Q squared is the same as alpha left minus alpha right. So alpha left is a section of degree 2 of the Lie algebroid. When I make alpha left, is a left vector field on G of degree 2 minus alpha right. So this is a multiplicative vector field of degree 2 on G, and I imposing that Q squared is equal to that degree 2 multiplicative vector field, and I imposing this other compatibility, that the bracket of Q with alpha left is equal to 0. So this is just the Lie bracket of vector fields on G. And this second equation here is what is the compatibility condition between the trilinear natural transformation in the definition of Baez and the bracket. So you see that complicated equation, it converts into a really simpler equation using graded geometry. So graded geometry is really powerful sometimes. And the second thing is that you see why alpha is a natural transformation. So you can see it that alpha is like a natural transformation between Q squared and 0. Since it's a natural transformation between Q squared and 0, it takes values into the kernel or into the core of that VB-groupoid, and the core of the VB-groupoid is the Lie algebroid shifted by 2, and this is why alpha can be seen, or is, in fact, a degree 2 section of the Lie algebroid. Okay, so this
yeah. Here, what was this?
Oh, I
Q
didn't.
alpha equal to 0, bracket Q alpha equal to 0 in the case of basis.
Yeah,
I
so
didn't see it.
So this equation, Q alpha left equal to 0, the bracket of Q alpha left equal to 0, is the same as this big equation here. The compatibility between the alpha and the bracket in this case.
The Jacobian, okay.
Yeah, is this higher coherence compatibility.
That's nice.
Okay. So you see this equation for sure looks more difficult, let's say, to remember that Q alpha equal to 0, that the bracket of Q alpha equal to 0. So this is why I'm saying that sometimes graded geometry helps you. Because this equation...
and Q squared is not 0 because it's somehow it's not double.
Yeah. Yeah. Q squared means that the Jacobiator is controlled by the natural transformation.
Yeah, double.
So, okay. So, and the second thing that I want to mention, because will be important, is that we can also define, or we need to define, what are morphisms between quasi-Q groupoids. And they are pairs of things. One is just a groupoid morphism. So this is just a graded manifold morphism between the groupoids. And then I have this R that is a natural transformation between these two functors, satisfying some higher compatibility with the alphas. So, okay, so we have now a tentative definition of what a Stacky Lie algebroid should be, but it's in graded geometry terms. So let's try to unfold our definition. So for that, just recall that I already said that given a VB-groupoid, then you have a degree 1 groupoid just by taking, these vector bundles define a degree 1 manifold, these other vector bundles define a degree 1 manifold, and then since it's a VB-groupoid, that means that you have a groupoid structure in the category of degree 1 manifolds. Okay, so a quasi-LA groupoid structure on this VB-groupoid is just a quasi-Q groupoid structure on this degree 1 groupoid. This is the definition of quasi-LA groupoid. So if we try to unfold just more and more, that means that H over G, this vector bundle, carries an anchor and a bracket. That is the structure of the Q. But now the alpha gives you also a 3 bracket that controls the Jacobi, and a kind of 2 anchor that controls the failure to be the anchor being bracket preserving. So now the anchor, that is something that goes from the H to the tangent of G, will not be bracket preserving, but there is a 2 anchor that controls that, and there is a 3 bracket that controls the failure of H of the bracket being Jacobi. And you have many equations that this object satisfied. We can have a theorem doing these kind of things, but I prefer not to put it because it's a bit difficult. But in the case where the base is just the identity groupoid, that is what we need to define a Stacky Lie groupoid, Stacky Lie algebroid, sorry, then if you just unfold the whole definition, what you have is a VB-groupoid over the identity groupoid, and then you have a bracket and an anchor that forms an almost Lie algebroid, and you have a vector bundle map from the wedge 3 of the side into the core, where C is the core of the VB-groupoid, and they satisfy these 4 properties. One, there is a compatibility between the almost Lie algebroid structure and the groupoid structure. Second, the Jacobi of the bracket is controlled by this map. Third, there is a compatibility between the anchor and the map. And fourth, there is this higher compatibility condition as in the case of Bayes and Kranz over a point. So it is just the same equation. And finally, I want just to say that morphisms can be also reinterpreted in classical terms, as we want. So this is the definition of what this quasi-LA groupoid over the unit classically it is. And this more or less horrible thing. But in graded terms, it's really easy. And now that we have this definition.
Sorry, Miquel, what is an almost Lie algebroid?
Oh, it's just, a bracket and an anchor that they satisfy, the bracket is skew symmetric, the anchor and the bracket satisfy the Leibniz property, and I think that's all.
Okay, thank you.
Yeah. Okay, so right now we are upstairs. So as we already announced, what we need to go downstairs is just doing the Morita class of this thing. So right now, amorphism between quasi-Q groupoids is say a Morita map if this F part is just a VB Morita map as defined by Deloyo and Ortiz. And then two quasi-LA groupoids over the unit are said to be Morita equivalent if there exists a third one and Morita maps such that Morita maps on the base are equal to the identity. So on the base, they are identities. And on the top, they are VB Morita maps that can be, relating H1 and H2 via this H3. And finally, we have that a Stacky Lie algebroid over M is the Morita class of a quasi-LA groupoid covering the identity groupoid M. So this is our definition of what a Stacky Lie algebroid is. And maybe right now is a good moment to ask questions, if there are some questions. Okay.
Yes.
Yeah.
If I may.
Can I ask something?
Yeah.
I think there was another question before Matthias.
Okay.
One second.
Sorry.
Okay. Yeah. If I may.
Yeah. Hi, Dima.
Yes. So since Stacky Lie groupoids are essentially the same thing as Lie 2 groupoids, certain contemplational manifolds, then wouldn't your Stacky Lie algebroids, like however you define it, basically come down to the same thing essentially as Lie 2 algebroids? And if you want to think in differential graded terms, then what that means. It's just
I will prove it
manifold.
I will prove it that in a moment.
You'll actually, you will prove it.
Yeah, it's like in two slides.
So you're not. Wait, I thought you said just for a second there. I thought you meant that this is the end of the talk.
No.
So you said, well, you can ask questions, but
yeah, I think that.
All right, so maybe then I'm kind of getting ahead of you.
Okay, yeah.
But yeah, and so then, well, I mean, there's something that for simplicial manifolds, I think something that Pavel Shavera like 15 years ago, and if you want to look at that in these double groupoid-like terms, then I think Madeleine Yotes has done some interesting work.
Yeah, we can discuss that, but I will prove it. Yeah. I just mean that because right now I will start to give properties of this Stacky Lie algebroid. So, yeah.
All right. Anyway, I'm sorry for the misunderstanding. I kind of thought that you already done. So.
Yeah.
Okay. So go on.
Could you also define this Stacky Lie algebroid by just a stack over M?
Well, we don't know how to make it yet, but I hope there should be a definition like that. But right now, the definition that we are proposing is that a Stacky Lie algebroid is the Morita class of one of these quasi-LA groupoids over the unit.
Yeah, that's what it should be. Too.
Yeah, we don't know the other definition, but I'm completely sure that should exist.
Right, it's hard.
Matthias, I think.
My question is that, well, in this paper with Christian, we show that if you look at VB groupoids up to these Morita equivalences, then this is like a Morita invariant. So if you take another group in the base, you are going to have the same, essentially the same VB groupoids. And it is not clear for me now if these structures that you are considering, these Stacky Lie algebroids, can also be pulled back and pushed forward from one base groupoid to another. Is it that possible?
Well, this is something that we don't know right now. This is why we are focusing in Stacky Lie algebroids and not in general Lie algebroids over differentiable stacks, because these kind of things appear.
Okay.
Yeah. Okay, so let's right now go to some properties of these Stacky Lie algebroids. And the first property is that one of Reutenberg was mentioned. So I was saying all the time that there must be a correspondence with some kind of two objects defined as simplicial thing. So let me define it right now. So an n-term L-infinity algebroid is a non-positively graded vector bundle together with an anchor and many graded antisymmetric brackets satisfying these higher Jacobi identities, okay? And well, it is known for n equal to 1, we have the definition of a Lie algebroid, and for n equal to 2, we have this two-term L-infinity algebroid that is the relevant object for this talk. And this consists just of a two-term complex of vector bundles together with an anchor and a bracket. And I have a sort of A0 connection on A1 and a sort of 3 bracket that is controlling the failure of Jacobi and the failure of this connection B flat. This is more or less what a two-term L-infinity algebroid is. And then we have these two results that are that there is an equivalence of categories between n terms L-infinity algebroids and degree n Q manifolds. And this was given by Bonavol and Tamponsin. And basically is what happens for Lie algebroids. You just need to look into the differential complex or given by the Chevalier-Eilenberg differential. And this is the Q manifold associated with the n-term L-infinity algebroid. And the second thing is that it is known that the infinitesimal counterpart of Lie2 groupoids, in the simplicial sense that I was explaining, are two-term L-infinity algebroids. And there are many works trying to explain this relation. And I want to say that this is more or less done, but there is still some details over there to be done. So our thing right now is just that I want to relate these two-term L-infinity algebroids with my previous thing because we have this guiding theorem. So how is this done? Well, this is done using this other result of Gracia, Saf, and Russian Meta that says that VB-groupoids corresponds to two-term representation up to homotopy of the base groupoid. Then, if in the base groupoid I just have M, the identity groupoid of M, what happens is that a two-term representation up to homotopy of the identity is just a two-term complex. So there is no higher actions of the groupoid, or it's just two vector bundles and a vector bundle map. This is the same as a two-term representation up to homotopy of the identity groupoid. And then we have our theorem that says that there is a one-to-one correspondence between quasi-LA groupoids covering the unit groupoid and two terms L-infinity algebroids. And this is using this decomposition of VB-groupoids into representations up to homotopy, into this complex. Moreover, and this will be really important, the quasi-LA groupoids are Morita equivalent if and only if the two-term L-infinity algebroids are quasi-isomorphic. So Morita equivalence for quasi-LA groupoids give you quasi-isomorphic L-infinity algebroid. And just I want to just point that this is really the infinitesimal counterpart of the Sue's guiding theorem relating Stacky Lie algebroids and two Lie-2 groupoids. And now, if we use all the correspondence that we have, we can see that there is a one-to-one correspondence between the following sets: Stacky Lie algebroids, 1, 2, Morita classes of quasi-Lie groupoids over the unit groupoid, 3, quasi-isomorphist classes of two-term L-infinity algebroids, 4, isomorphist classes of degree 2 Q manifolds, or even 5, isomorphic classes of VB current algebroids. And the way to pass from one to the others is, for example, let's start here in 3. Suppose that I have a two-term L-infinity algebroid, then the theorem 1 tells me how to construct the associated quasi-Lie groupoid, and then by definition, this gives me an Stacky Lie algebroid, and everything is fine because quasi-isomorphisms correspond to Morita classes. That is the definition of a Stacky Lie algebroid. But going into the other direction, I can use this Bonavolon-Taponsin theorem and define a degree 2 Q manifold. And even more, David LeBlanc proved that degree 2 Q manifold corresponds to VB current algebroids. And here is where the VB current algebroid is defined. So all these 5 things are the same. And I just want to point here that I say here sets, but in fact, I think that maybe one can say that these things are categories or maybe 2 categories, and there is an equivalence between 2 categories of these 5 things. Okay, and the second property that I want to mention is, given a Lie algebroid, the dual is a linear Poisson manifold, a linear Poisson vector bundle. And I want to say something similar for Stacky Lie algebroids, and then for that, I need to introduce what a quasi-Poisson groupoid is. So this was introduced by Iglesias Ponte, Camille Laurencecho, and Ping Xu. And they say that a quasi-Poisson groupoid is just a Lie groupoid endowed with a bivector, with a multiplicative bivector field, and a section of the wedge 3 of the Lie algebroid satisfying these 2 equations that, as you see, are basically the same as equations for quasi-Q manifolds. So recently, Ping Xu and Camille, with 2 other collaborators, Bonecki and Nicola Schicoli, defined one-shifted Poisson differentiable stacks as the Morita class of quasi-Poisson groupoids. Okay, and now what we are able to use is that result in order to see that the dual of quasi-Lie groupoid is a linear quasi-Poisson VB groupoid, because recall that VB groupoids have dual objects, where I just take here the dual of a vector bundle, and this is the dual of the core. And now linear means that, the top groupoid is a quasi-Poisson, and the 2 tensors are linear tensors with respect to the vector bundles structures over there. So putting all together, we can see that the dual of a Stacky Lie algebroid is a linear one-shifted Poisson stack. And what one needs to see here is that Morita equivalence here in this side is the same as Morita equivalence for quasi-Poisson groupoids in the other side. And this is true because on the base, we have identities. And then you know that Lie algebroid morphism and Lie algebroid comorphism over the identity coincide, over the same base coincide. And this is really important also to have this theorem over here that we are considering Morita maps that are identities on the basis. But then we have this just analogous theorem for Lie algebroid, that is that the dual of a Stacky Lie algebroid is a linear one-shifted Poisson stack. Okay, and then just to finish, I want to comment on this work in progress part, on this S-Lie functor and the integration of current algebroids. Okay, so recall that up to now, Chen and Sen defined these Stacky Lie groupoids, and right now we defined these Stacky Lie algebroids, and we want to see if there is some Stacky Lie functor relating both categories. So the strategy here is just use this definition using doubles. So Stacky Lie groupoids must coincide with some quasi-double groupoids over the unit modulo Morita, and then we will use some quasi-Lie functor, and then we came back to a Stacky Lie algebroid. We can produce a Stacky Lie algebroid. This is the idea of the strategy, how to go from a Stacky Lie groupoids to a Stacky Lie algebroid. The point is that these quasi-double groupoids over the unit are not already defined, and I think that this is part of what Matthias was asking, and this is something that we are trying to do right now, defining these quasi-double groupoids over the unit, or maybe in general, I don't know. So, but we believe that with these quasi things, it's easy to prove that this S-Lie functor exists in the differentiation to prove some infinitesimal differentiation, to construct a Stacky Lie algebroid for any Stacky Lie groupoid. Okay, for the integration, we don't know anything right now. This is really like the plain answer, but I can say something. For strict ones, when you drop this quasi thing here, it is possible. Because for strict ones, this is the same as a Lie algebroid and a flat vector bundle. Then Lie algebroids integrate to dual Stacky Lie groupoids, and it is easy to see that the flat representation also integrates to this Stacky Lie groupoid, to a representation of this Stacky Lie groupoid. So for strict ones, it's really easy to see the integration, but for the non-strict ones, we don't know anything. Even in the case where M is a point, we believe that it is known, but we couldn't find any direct proof in the literature. So maybe someone in the audience known and can say me, can help us with this. But the point is that there are many definitions of what a semi-strict Lie2 group is, and well, there are different proof of different objects of things. So we are really glad if someone can point us where to find the proof, even in the case of a point. And finally, just to say, okay, there are topological obstructions or there are not. So we don't know. I couldn't say anything. My guess right now is that there are not topological obstructions, but you see, it's just a guess. I have no idea really. So okay, and just the last thing that I promise is about this integration of current algebroids and what have to do with all what I mentioned. Okay, so this is because there is this correspondence, this Severa-Reutenberg correspondence that states that there is a one-to-one correspondence between current algebroids and degree 2 symplectic Q manifolds. Then, by this corollary of the multiple equivalence that I mentioned, we know that degree 2 Q manifolds corresponds to a Stacky Lie algebroid. Moreover, this Stacky Lie algebroid, since this degree 2 Q manifold is symplectic, must carry a compatible two-shifted symplectic structure. So maybe some kind of Stacky bialgebroid or something like that. And then, from this point of view, what we propose here is that current algebroids should integrate to two shifted symplectic Stacky Lie groupoids. That's our proposal. And well, why this is a bit different of what was proposed right now is because this two-shifted symplectic Stacky Lie groupoid can be thought of a sort of quotient of the two groupoid, of the symplectic two groupoid integrating the current algebroid. Hence, there are more chances to be finite dimensional and really to this degree two shifted symplectic Stacky Lie groupoid be really good defined, well defined for any current algebroid. And this is why we believe that is a good candidate to integrate current algebroids to something finite dimensional. And the last thing that I want to point is that the symplectic structure is two-shifted because tangent and cotangent complex of current algebroids have length 3. And there is enough room to have two-shifted things because we have a groupoid object with differentiable stacks, and then we can have two-shifted symplectic structures. That is something that is not, as far as I know, already defined for differential geometry objects, but we have more or less a close definition that I hope will present soon in some other seminar. And well, that was all. Thank you very much for your attention.
Thank you.